Right. Assalamualaikum and good afternoon, everyone. So, welcome for today collaborative teaching session on properties of good estimator under the course of STA 256 Mathematical Statistic 2. So, I am delighted to moderate this session, which is a joint effort between University Teknologi Mara and Universiti Kebangsaan Malaysia. So today we have a privilege of learning from esteemed expert from the field of statistics. His field of statistics. I am encourage you during the lecture. You all can actively participate, ask question, and make the most of this opportunity. Right. So without further ado, let me introduce our distinguished speaker. So we are honored to have Dr. Muhammad Irfan Abdul Jalal as our guest lecturer today. Dr. Irfan is actually a senior lecturer at Institute of Molecular Biology, UMBI, Universiti Kebangsaan Malaysia. So with over 8 years of experience in as a medical statistician, he specialized in applying advanced statistical methodologies, including Bayesian statistics to clinical research in oncology and therapeutic drug monitoring. So holding a PhD in statistics from Newcastle University, Dr. Irfan brings a wealth of knowledge from his extensive teaching, research, and publication record. So his expertise in statistical software and his dedication to postgraduate supervision and undergraduate teaching make him an invaluable contributor to this session. So please join me in welcoming Dr. Muhammad Irfan Abdul Jalal for delivering his lecture on properties of good estimator. So the floor is yours, Dr. Irfan.
Okay, thank you, Dr. Muhammad Nasir. Assalamualaikum. Thank you for the kind introduction. My name is Dr. Irfan. I'm from UMBI, Institute of Molecular Medicine at UKM. So I've been a medical statistician for nearly 8 years, and I've been collaborating with Dr. Muhammad Nasir in several research projects previously. So without further ado, then we just go straight into the lectures today, because we are running out of time. So let me share my slides first. Okay. Can you see my slides now?
Yeah, sure.
Sure. Okay. So today we'll be learning about the properties of estimators. Before we start, so I will give a brief introductions on the properties of estimators. As an introduction, the key concepts for our today's lecture is the estimator is, as you have learned before from Dr. Nasir's class, an estimator is a function of a random samples. Therefore, because it consists of the estimator is a function of random sample, therefore it itself can be considered or can be treated as a random variable as well. So why this matters? Because we have lots of some critical problems in statistics where the major challenge when we obtain or we calculate the point estimation to represent our data is we want to understand the sampling distribution of the estimator that we will use for summarizing our data, for example. So the distributions of this sampling of the sampling distributions of this estimator will tell us, in the long run, how the behavior of these estimators across repeated samples that were obtained from the populations. As a trivial example, as an easy example, for example,
Dr. Irfan,
yes,
your slide tu tak bergerak
tak gerak tak gerak Ni gerak tak?
Tak,
Tak gerak Okay,
tak
wait.
gerak. So maybe you can share screen saja instead of sharing the slide.
Okay, stop sharing. Share entire screen
Yeah.
Okay, can you see my slides now?
Okay, can you move the slide? Okay. All right.
Okay, all right. Okay. So Okay, these are the things that I introduced just now, the key concepts and why this matters in statistics. So as an example, if you want to estimate the population variance or your population's dispersion parameters, then we usually we use a sample variance that we calculated using your usual formula that you have learned previously from descriptive statistics. However, unlikely that the values from the sample variance that we calculate from a single sample, single sample from the data that you obtain from that you sample from the population will be exactly or accurately equal to the true population variance, which is represented by the sigma squared here. So as a result, it's important to know whether the sample variance that you use to estimate the population variance is on the long run or in average on average will be close to the population variance. And then if you use different samples, you take another sample number 2, sample number 3, sample number 2, number 3, and you want to see whether the sample variance is actually as close as to the population variance or not. For example, kalau saya buat research and then saya nak tengok what is the the variance of blood pressure, for example, in the population. In the population, I want to estimate the blood pressure's variance in the populations. Then I use the samples variance of around 100 patients or hundreds in the healthy individuals in my populations. And then I compute sample variance for my samples, which is around like 100 patients. And then another researcher comes in, and then they took another 100 samples. This will constitute as a second samples, and they compute the second sample variance. And then another researcher, the third researcher comes in, and then he samples another 100 patients or individuals from the population and computes the third sample variance. So we want to see this sample variance, how these three sample variances, how they they behave in the long run, whether it's very near or very far from the population variance. And because of this, we need to learn the properties of estimator. Because we want to understand, for example, what is the behavior of the sample variance in the long run. If you use a lot of sample, whether it can closely estimate the population variance or not. So for example, there's another example. This is a decision problems kind of example. Suppose we need to decide whether to use the sample mean or the sample median to estimate the population mean of a condition of interest. For example, the example that I gave you previously is to estimate the population mean of blood pressure or perhaps a glucose level in individuals or in patients with type 2 diabetes mellitus or kencing manis jenis kedua. So we want to know which estimator, either the sample mean or the sample median, will be more accurately to represent the true population mean. So since both population sample mean and sample median can be calculated from the data that we obtain from the population and therefore are considered random variables, their sampling distributions of this sample mean and the sample median will help us to evaluate the performance, their individual performance as estimators of the population A. So sekarang kita ada some decision that we need to make. Kita nak choose the sample mean or the sample median to estimate our parameter of interest, which is the population mean of, for example, the blood pressure or the glucose level of patients. So benda ni kita boleh represent in a nice diagrams. So sampling distribution of the sample mean, for example, this is actually the dot here itu can be considered as the true population mean of the systolic blood pressure or the blood pressure of individual, for example. So katakan kita ambil I as the first researcher compute the first sample mean. And then the sample means is around this region. And then Dr. Nasir takes another 100 participants, and then they compute the second sample mean, and then he got the sample mean of this blood pressure around here. And the third researcher comes in, another friend of mine, he computes another sample mean, the third sample mean, and then it's around this region. So we want to know whether the sample means or the sample medians here will be the beta estimator, will be the beta estimator of the population mean of blood pressure, for example. So in this case, which is more likely to be close to the population mean? Is it the median mean or the median, the sample mean or the sample median? As a result, we need to examine the sampling distributions of this mean and the medians. This is the decision problem. As another example, we all mean as another issue. Another challenges in the estimated theory is we also have different estimators for the parameter of interest, for our parameters of interest. For example, for a uniform distributions, we have the maximum likelihood estimator, or the MLE, and then the moment estimator that for estimating the parameter theta, which is unknown parameter for these uniform distributions. So as a key point, different estimation methods can lead to different estimators for the same parameter. So kalau kita pakai maximum likelihood estimations, and then we also use a method of moments, we obtain like two estimators of the parameters theta here. Because we use different methods to estimate the parameter theta, one is MLE, then the other one is moment method, MOM methods. So the result will be different, even though it's for the same estimator. So as an example to illustrate this point, consider a uniform distribution which is given by by these equations 1 over theta, where the bounds for the observation y is between zeros and theta here. In other words, the random variables y1, y2, y3 until yn is distributed as a uniform distributions with a parameter 0 and theta. And then because of this, we want to estimate theta based on a sample. So there are two types of estimators for estimating theta for this uniform distribution. The first one is the MLE, maximum likelihood estimator. And based on the distribution theory that you have learned previously for the uniform distribution, the estimator, the MLE estimator for this uniform distribution is the maximums of the observation, the largest value for the observations, or for the data. For the data here, 1 to y2, y1, y2, y3 until yn here, you choose the maximum ones, and then the maximum value is the MLE estimate for parameter theta here, as you can see from my arrow there. But there's also another method to estimate theta for the uniform distributions, and then it is called methods of moments, where based on the equations, based on the results they have known, then the estimator, the moment estimator for theta is given by this equation 2 over n with the summations of the times by the summations of the observations that you have y1 plus y2, y3, y4 until yn. So in this case, which estimator is better? Is it the MLE estimator or the moment estimator? To choose which estimator is the better ones, so we need to evaluate the MLE estimator and the moments estimator based on these four properties. The first one is unbiasedness. The second one is consistency. The third one is sufficiency, and the last one is efficiency. These are the orders of the of the properties that we're going to discuss, or that will be elaborated today. During the lectures. Okay, so always remember these are the four important properties of estimators that you need to use or you need to employ when you want to see the performance of the estimator. Which one is better? Estimator for the population parameter of interest. The first one is, as a recap, unbiasedness, unbiased properties of the estimator, the consistency of the estimator, the sufficiency of the estimator, and the efficiency of the estimator. So we're going to go into the first one, definition one. The first one is unbiasedness. Definition one, a statistics or call it an estimator theta hat is an unbiased estimator of the property of the parameter of interest, which is theta, if only if the expectations of the theta hat here, the expectation of the theta hat, of the average of the theta hat, for example, the average of your the sample means of the sample means will be equal to the true parameter theta here. If the expectation of theta, I mean, does not equal to theta in the long run, then the theta hat, or the estimated theta hat is said to be biased in this case. This bias means that it will not accurately on the long run or on the average will not manage to estimate the theta accurately. For example, as you can see from the distribution curves here, for an unbiased estimator, the average or the expectation of the estimator, for example, theta here, will equal to the true values of theta. This is the actual value in the population. For example, based on the example that I gave you just now, for example, in the long run, there are like 3 sample means that we computed based on 3 different samples. Each has 100 subjects in the samples. And in the long run, if the sample mean is an unbiased estimator of the population mean, for example, then in the long run, if you compute it on the average, then it will manage to accurately estimate the population mean, for example, of the blood pressure in healthy individuals, for example, in Perak. Okay, but in this case, you can see that this is the estimator, the average value of the estimator. It really coincides with the actual value of the population parameter of interest. For example, the population mean of systolic blood pressure or the blood pressure in healthy individuals in Perak. But if the estimator with the sample mean is for example, is a biased estimator of the population parameters, is in the long run it will not be able to estimate accurately the population parameter. So it will be on the average the sample mean will have around this value, whilst the actual values for the systolic blood pressure is actually around here. So it always tends to overestimate the actual value of the systolic blood pressure. Because of this, then the sample mean, for example, if the A is an example, as an example for A is like the sample mean can be considered as a bias estimator of the population mean, or we can say that the sample medians. Okay. So in definition 2, is also important definition. Suppose that the random variables or the data, the random variable or the data, y1, y2, y3, and until yn is a random sample from the continuous probability density function fy given theta. Theta is the parameter where theta is an unknown parameter, and an estimator of this theta, the theta hat here, is said to be unbiased for theta if, again, expectation for theta is of theta hat or the estimator equals to theta for all theta on the long run, in the long run, and then on the average. And then this concept, the same concept and terminology can be applied if the data consists of a random sample drawn from a probability mass function or from discrete PDF fx given theta here. So to illustrate this further, for example, I give you a medical example based on my previous research, where we have a research to estimate and the average mean systolic blood pressure of all male adults. Actually, I'm put a Perak here, but actually we try to estimate the average systolic blood pressure or the blood pressure of all male adults in Klang Valley actually. So, but because you are based in Tapas, so I just changed the example a bit here. So solutions, let the true population SBP, the systolic blood pressure here, is represented by notation here is notated by mu, which is unknown. That's the true population mean blood pressure that we want to estimate actually. So we take a random sample of size n patients from this population, from the populations of male adults in Perak. Then we measure their blood pressure for the first sample, the second sample, until sample number n. So we use the sample mean SBP. We compute the sample mean SBP using this formula, well-known formula here, and as our unbiased estimator for population mean systolic blood pressure. So imagine that this is based on a random sample. Imagine we repeat the above studies 1,000 times. Actually, for example, we take n number of patients from these populations, different n patients from this population 1,000 times. For example, if the sample size is around 100, so we take hundreds samples 1,000 times from the population. So as if we repeated the studies 1,000 times. So in other, in other analogy, for example, I have like 1,000 researchers. So each researchers take 100 patients from this population and computes the SBP for each sample. So we now have 1,000 sample means of the systolic blood pressure. So if the sample mean for the systolic blood pressure is an unbiased estimator for the population mean of the systolic blood pressure or the blood pressure, then the average or the expectations of this 1,000 sample mean of the systolic blood pressure will be the true value of the population systolic blood pressure that we are trying to estimate. So that's the basic of it as an example. For example, in this case, as a further illustration, for example, this is the mean systolic blood pressure that you want to estimate. So we have like 1,000 means from 1,000 samples, different samples, each consisting of 100 patients, for example. So we have 1,000 sample means. For example, that means one sample will have a mean around here, another sample mean around here, and my sample has a mean around here, and Dr. Nasir's sample has means around here. And then the friends of mine has a mean around here. So we can get this kind of distributions. So if the sample mean is really an unbiased estimator of the population mean, then on the long run, if you average all the sample means here, then it will be very close to the mu or the population mean of the systolic blood pressure here. So it can be, so this is when the estimator is considered unbiased. But if the estimator is biased, then we can see from here, a biased estimator will tend to either overshoots or exceeds the the true values of the population mean in the long run, or the results will be less than the true population value of the, for example, systolic blood pressure, the parameter of interest here. So as you can see here, the center of it is less than theta, and then it doesn't the distribution here for the bias estimator, for example, like the sample median, for example, will not be able to capture the population mean here. So that's another visual example. All right, so we go straight to the to mathematical examples how we can prove certain property. Certain statistics or certain estimator is an unbiased estimator of the population parameter of interest. So this example 15, for example, if x, the random variable x, has a binomial distribution with the parameters n and theta. So we want to show that the sample proportion x over n, which is the x is the number of success. For Bernoulli trials, we call that, for things that can be yes or no kind of things, is an unbiased estimator for theta. Okay. So the solution, I always put that in steps so that you can understand the solutions are better. So first one, we need to start with step one, definition of unbiased estimator. So again, an estimator theta hat is considered an unbiased if for a parameter theta, if the expectations or on the long run, on the average of this of the estimator will be equal to the true parameter theta. For example, in this our case, we call it the sample proportion here. In the long run, if we compute lots of the sample proportions sample proportion for this condition of interest, the long run it will be equal to the true population proportion, for example. So step two, we need to extract the information from the question. The first one is, x is distributed as a binomial, in a binomial manner, in a binomial fashion, where the parameters is n, and then the probability of success is theta, p here. So again, for the binomial distribution, you understand, you have perhaps you have learned about this, in previous lecture, that the expected value of a binomial random variable is ex equals to n theta. So the proposed estimator is the sample proportion, which is theta hat equals to xn, equals to x over n. Okay. So again, we can compute step 3. We compute the expected value of the estimator, because we need to show this one. The expected value of the estimator will be will be equal to theta or not. If it equals to theta, then it's considered as an biased estimator. If not, it does not equal to theta, and then it's not a bias. It's a bias estimator. So using the well-known result for expectation, using the linearity of expectation. So expectations of theta hat, which is the sample proportion x over n, equals to 1 over n times by ex, by the expectation of x. So this is based on expectation ax equals to a times expectation of x, times expectation of x. Okay, so you factor out this one, so it becomes like 1 over n times x. X is the random variable, so you move it aside here, so it becomes 1 over n. Then x is the random variable, so ex. So again, what is the ex? So ex based on the expectations of the binomial random variables here, n theta. So we substitute ex with n theta. So you can cancel out these two terms. So it becomes like theta. Theta times 1 becomes theta. So ex over n equals to theta. So as a conclusion in this case, since ex expectation of x over n, the sample proportion equals to theta, then we can conclude that the sample proportion x over n is an unbiased estimator of the population proportions of the condition of interest. So this is the example 15, the solution for example 15. Okay, so we move to example 16. So in this case, the question is a bit different, where we need to show that unless that theta equals to 1 over 2, the minimax estimator of the binomial parameter theta, this quantity x plus half times by square root of n divided by n plus a square root of n is biased. So this is the condition that if the theta itself is equals to 2, then the estimator will be biased. Okay. So if theta equals to 1 over 2, then it's not it's an unbiased estimator. But if it takes other values other than half or 1 over 2, then the estimator here, the minimax estimator here will be a biased estimator. So again, recall from our previous example that the definition of an unbiased estimator is this one. And expected theta hat is unbiased for the true theta if it's unbiased estimator for theta if expectation of the estimator theta hat equals to theta. So we need to second step is we need to define the estimator. So in this case, the given estimator is a bit different. Theta hat equals to x plus 1 over half times by square root of n, and then divided by n plus square root of n, which is a function of the random variables. Again, x being binomial and theta. So using the linearity of expectation for step 3, we need to take the expectation for the estimator. We need to compute this part. Okay, we need to compute this part. In this case, the estimator is this quantity here. So using the linearity of the linear properties of expectations, then so we can move we can factorize. We can factorize 1 over 1 over n plus square root of n and put it outside, and then ex plus 1 to plus half over n the square root of n inside. So in this case, again, the expectation of x is n times theta, which is because this is a binomial because this is a binomial distribution. So we will get these quantities, okay, for the expectations of the estimator theta hat here. So after that, step 4, we need to determine the condition for unbiasedness. The condition we need to, when we test the condition for the unbiased properties of the estimator, we need to equal the quantity with a theta here. So from this is the expectation for the estimator here, and then we equal that with theta, and then we solve this equation algebraically. This is a very this is very trivial kinds of algebraic solutions for this for these equations. We need to solve it for theta. So after, we times this sides with n plus a square root of n, and then we'll solve it algebraically, and then we will obtain that the theta as equals to half. So in this case, we can make a conclusion that the estimator is only unbiased when theta equals to half or 1/2. And then another conclusion, we can say that for any other value of theta, which other values other than half, then the expectation of the estimator of this one, the expectation of this one will not equal theta, will not equal the true population's parameter of interest. So because of this, the estimator is biased when the value of theta is not half. So in other words, the estimator is biased if theta does not equal to half. So in this case, we prove that our task here, that the minimum estimator of the binomial parameter, this quantity is unbiased only when theta equals to half. If other values, then is considered as biased, because these values, then the expectation of this estimator will not equals to theta here. So it has a certain bias. So in the long run, if you compute all the sample, like 1,000 sample means, all those things, it will not converge towards your true population parameter. Okay, so this is another example 17. For the unbiased properties of the estimator. So in this case, we have n samples from an exponential distribution. We have x1, x2, x3, x4 until xn. And then this random sample behaves like a sample from an exponential distribution with parameter theta here. So in this case, we want to test whether the x bar here, the x bar, the estimated x bar here, which is summations of x1 until xn divided by 2, is unbiased estimator for theta. For theta of the exponential distribution here, the parameter for the exponential distributions. As you know, the exponential distribution has only one parameter here. So this one is for exponential distributions. So in this case, we need to write down the PDF or the probability density function for the exponential distribution first. So as you have learned from your previous lecture, hopefully, that the probability density function of the exponential distributions of a parameter theta here, with a parameter theta here, is given by these values, by these equations. So fx given the parameter theta is equal to 1/theta exponents of minus x over theta here. So as you know, the probability density function for the exponential distribution is always positive. It's always positive. It has a positive support. So x always can be zeros to any values. To infinities, for example. But it cannot take like negative values. And then the theta itself, we put a restriction or conditions here where the theta itself should also be positive values, all right? And then it cannot be zero, because if you put zeros here, then it can go to infinities. So it's not a true distribution anyway. So there's a limit here. Can be as small as possible, but cannot take zero values. So step 2, we need to write the estimator that we want to investigate. In this case, this quantity here. So the x bar is equal to 1/2 times by the summations of all the random variables there, x, I. And we need also to be careful here that this is not your usual sample mean. This is like a scale sum by factor of 2. So this is not your usual sample mean because it's not divided by n there. So take the expectation of the estimator. So again, using the linearity of expectation, so we can substitute the x bar here, the expectation of the estimator of interest, which is the x bar here, with these values. So again, using the linearity of expectations, we can move half outside, and nex can be nex, and then the expectation of x after that. Okay, since each xi is distributed as an exponential distribution with a parameter theta, we know that based on our knowledge on the exponential distribution theory that expectation of ex for is also theta for exponential distributions. So we can simply substitute theta here into here, and then because of that, then this is the expectations of the x bar, the expectation of x bar for this for these questions, which is n times theta divided by 2, because here we um, we substitute ex here, expectation of x here with theta there. Okay, so n theta divided by 2. So the step 4, we want to check whether the estimator is unbiased or not. So again, we need to equalize n over n times theta divided by 2 here by theta. But here again, we can see, from obviously we can see from the bird's eye view that expectation of x bar here is n theta divided by 2. Hence, unless n theta divided by 2 is equals to theta, this is not unbiased. So we solve the equation here, and then we can get that n equals to 2. So in this case, we can make a conclusion that only when n equals to 2, then the estimator of this and this estimator x bar is unbiased. For other values of n, for example, n1, n3, n4, n5, or so on and so forth, this estimator is biased. If you want an unbiased estimator for theta, you should use the sample mean. In this case, x bar equals to 1 over n times x bar, summation of x here divided by n. Your sample mean, usual sample mean, will be the unbiased estimator for theta, regardless the values for n. The proof for this is omitted, and because this is trivial, but you can try to at home and see whether this one is an unbiased estimator. This form of estimator is an unbiased estimator for theta instead of this one. Okay, I think I should put another notation here. For example, like x bar scale here, and this one is your usual x bar. So I will change the notation a bit so that you will not be confused. All right. So the last example for unbiased properties of the estimator. So again, we let's use a more familiar example in this case. So we assume that the data or the observations x1, x2, x3, the random variables until xn is a random sample from a normal Gaussian distribution where both the population mean and the population variance, the dispersion parameter here, sigma squared, are both unknown. Okay, so we have two estimators here. The estimator, the first one is considered as mu1. So sorry about this. This one is considered estimator because we have we have a hat here. Mu1 equals to 1 over 4 x1 times x1 plus 1 over 2 times x2 plus 1 over 4 times x3. But we also have another competing estimator, which is mu hat 2. In this case, where for x1, x2, x3, we x1 plus x2, x3 divided by 3. So we need, in this case, we want to determine which estimator is unbiased, or both estimators are unbiased, or both estimators are biased estimators. So in this case, this is the solutions. Again, always remember this part. Recall that the definition of an unbiased estimator is when the expectation of the estimator theta hat equals to theta. In our case, since the random variables comes from the Gaussian distribution or the normal distributions, then the mu1 and mu2 hat can be considered as two competing estimators for the population mean. For these Gaussian distributions. So we will compute their expectation for this one and expectation for this one, and check if they equals to mu. In this case, equals to theta here. So first we analyze the first estimator. In this case, it's a mu hat equals to this quantity here. because x1, x2, x3 are random sample from a normal Gaussian distribution with the same common mu, so we know that expectation x1 will be equal to expectation of x2 and will be equal to expectation of x3. So it will equal to a common mean of mu here. Hence, we take the expectations of mu1 like this. This is based on the linear properties of expectations here, because it's x1, we take expectation of this one, so it will be like 1/4 times by expectation of x1 plus half times expectation of x2 plus 1/4 times expectation of x3. So in this case, because they come from this the same common mu or common population mean, so we can substitute the values into here. So as you can see, 1/4 mu plus 1/2 mu plus 1/4 mu will equal to mu. So in the long run, therefore, this first estimator mu1 is an unbiased estimator of mu. Can be considered an unbiased estimator of mu. Okay, after that, we need to analyze the second estimator. In this case, mu2. So in this case, we have this this quantity for mu2. So this is just the sample mean of the first three observations. So mu2 can be considered as 1/3 x1 plus x2 x3. So again, using the linear properties of expectation, we will get the expectations of the estimator like this. 1/3 times expectation of x1 plus 1/3 times expectation of x2 and plus 1/3 expectations of x3. And again, recall that the expectations for all these variables x1, x2, x3, they comes from the same distributions. So the expectation of this will be mu. So you substitute mu into each of the expectation terms here. So it will be mu. 1/3 mu, the first mu, plus 1/3 mu plus the last 1/3 mu, so it will be equal to mu. So therefore, the expectations of the second estimator mu here will be equal to mu. So in this case, mu2, the second estimator can be also considered as an unbiased estimator for mu. So in this case, we can say that as a conclusion, both the first estimator mu1 and mu2 are unbiased estimator of mu. Okay. So now we are going to move into consistency of an estimator. Any questions before we proceed into the second one?
Any question from on the floor? Ada soalan tak?
So you want me to go over the things again? That's fine too.
If you
have any other questions, any question, that's fine. You can ask. If not, then we can move to the second part of this lecture, which is the consistency of an estimator.
Okay, students, if you have any question now, you can raise the question now, or if don't, we can proceed with the next properties, which is consistency. Yeah, Ali Matun.
So if an estimator is biased, how can we determine the extent to which its expected value derivative from the true population mean?
Sorry, can you repeat the questions again? Because some problem with connections.
So if an estimator is biased, how can we determine the extent to which its expected value derivative from the true population mean?
Okay, the extent of the biasness of the estimators. There should be like some, for example, like if you use like I can give you one example there. Okay, like this one. Okay, so in this case, for example, if the estimators here for this binomial parameter will only be unbiased when the theta equals to 1/2. So if you can always put like the you can always put like yes, you can always put like different values for theta here, and then because of this, because for example you put like another value here, for example 1/3 here, so 1/3, which is different to I mean to the value of 1/2, where the where call that, where the estimator becomes unbiased. So from this case, you can see that the estimator will not be equal to theta by some values by some values in the long run. For example, if we put like 1/3 here, 1/3 here. So after we solve the equation there, then we can have the values for the estimator will have some discrepancies with the theta. So that will be your bias, the degree of bias of your estimator can be considered like that. But again, based on certain theorems, we can examine for each estimator, for example, like the sample medians or this kind of estimator. We can see for each estimator they have some limits in terms of their biasness. To the parameters. But I can say that for each estimator, they have different degrees of biasness with some factors there. All right. Yeah, do you understand, or you want different explanations for that?
Okay, I understand. Thank you, Doctor.
Okay. Okay.
I think there are no more questions. Dr. Irfan, if you want to take a 5-minute breaks or 10-minute breaks for them to digest the first part of the topic, it's okay. Ataupun you nak continue?
Boleh.
Sorry.
Yes, Nur Ain.
Can you repeat example 18?
Example 18.
Yes.
Okay, which part? You want to copy the solutions, or you want me to explain over the solutions here?
Re-explain.
Re-explain. Okay.
Yes.
Okay. So in this case, I mean, as a recap, as a summary, we have like two different estimators for population mean. Okay. So this is the first estimator. This is the structure of it, or the equation of it. And then the second estimator is this one. Okay, this one is just more like a sample means of your first three three samples, for example. This one is like your weighted sample. We call that the weighted sample of your first three samples, because I mean the weights here is different for sample 1, sample 2, and sample 3. So in this case, we want to know whether the weighted samples, the weighted sample means, or your sample means, your usual sample means here, are they both biased, or they both unbiased, or they both one of them biased and one of them is not biased, one of them biased and one of them unbiased. So again, we have to recall the definition of an unbiased estimator like this. Expectation of the estimator equals to theta. And again, as another example, another explanation for the first questions, the bias of the estimator is given by, for example, like I put a bias here, bias square, put a bracket there, theta hat here will be expectations of theta hat minus the true theta there. So that will be the bias. So the bias will be some values. That's the discrepancy that I told you before. So that's how you calculate the bias. Okay. I mean, these things have been used in machine learning quite a lot. So in our case, both estimator, the first version, mu1 and mu2 can be considered as two competing estimators for mu. Maksudnya kita ada dua choices here. Kita ada dua pilihan. Kita nak consider ni mu1 ke ataupun mu2. I mean as the unbiased estimators of mu, ataupun dua-dua pun sebenarnya unbiased estimator of mu, which is in the long run kalau kita compute in the long run benda ni dia akan hit kepada population parameter of this mu. Okay. So in the second step selalunya saya akan buat macam ni. So kita analyze the first estimator first, okay? So again kena recall balik the first estimator is this one, 1/4 x1 plus 1/2 x2 dan plus 1/4 x3. Disebabkan apa semua, I mean the tiga sampel ni, all these three sample ni are random variables or random sample from a normal, ataupun another word for normal is called Gaussian distribution, dengan satu parameter yang sama untuk average, untuk population average dia, which is mu. So expectation untuk this random variable 1 will be the same as the expectations of this random variable 2, and then the expectation of random variable 3, which is mu, because they come from the same distribution with a common population parameter here. So because of that, kalau kita ambil expectation of this one, so it will be like expectation on the left side here, the first estimator here, then it will be like 1/4 times expectation of this random variable plus half expectation of this random variable, and then 1/4 expectation of this random variable here. So kita tahu the expectation for all these three random variables, they are the same. So we just substitute that into this one. So dia akan jadi macam ni, 1/4 of mu, because kita substitutekan ni masuk dalam ni, plus 1/2 half of mu, and plus 1/4 of mu equals to mu. Therefore because of expectations of this estimator, mu1 hat ni sama dengan mu here, so they can be considered as mu hat ni as an unbiased estimator of mu because it fulfills this condition. Expectation of theta hat ni can be considered as the general notation for any estimator of your interest, sample mean ke sample variance ke whatever, we must be equal to theta, which is can be your population mean ke population variance ke apa semua. So as you can see that mu here, expectation of this is also mu, so mu ni actually equals to mu. So that's the reason why the estimator or the first estimator can be considered as unbiased estimator of mu because it fulfills this property. Okay, understand? Boleh yang ni?
Boleh.
Okay, so lepas tu kita move to the step 3. Step 3 we analyze lah the second one, the second estimator lah, yang this one. Kita buat satu-satu lah lebih kurang. So for the third step, kita pun cuba analyze using the following, using the same logics or using the same, the same cara lah, the same method for step 2. So untuk this one, kita take the expectation of the second estimator on both sides. So kita akan dapat these things, and again kita kena recall balik because it comes, the random variable comes from the same distribution with a common mu or common population parameter. So kita substitute this into this one. So again, the expectations of the second estimator to will be equal to mu because it also fulfills this property here, because expectations of the second estimator ni equals to mu here, and then the theta, the actual one pun also mu. So therefore untuk second estimator pun it can also be considered as an unbiased estimator of mu. So as a conclusion, kita boleh cakap both estimator this form, this form and this form as unbiased estimator untuk our parameter of interest. Okay. Boleh faham?
Faham?
Okay. So that's the conclusion. Nanti untuk soalan yang pertama tu nanti saya akan bagi another, because this part based on the lecture punya slide previously is not covered. So nanti untuk that part tu nanti saya akan tambah another slide here to show example. Tak apalah, kita kira example 18B untuk calculate macam mana the factor untuk some bias estimator. Okay. For example, untuk kalau kita selalu gunakan untuk kita calculate macam variance kan, kita 1 over n minus 1. So I will show you macam another version of the estimator for the population variance tu is like 1 over n. Kenapa 1 over n tu is 1 over n tu is a bias estimator for the population variance. Then you can see that okay, based on the calculation tu apakah berapa jauh dia punya beza kalau kita guna sample variance tu kita divide by 1 over n instead of 1 over n minus 1. Kan kita ingat kan xi minus x bar lepas tu square, we can take a square and then we sum that and then we divide n minus 1. So that can consider as your usual formula for variance, sample variance. Tapi another competing formula ialah kita divide those things by by over n. Yang tu akan results in some biasness, and the biasness tu ada dia punya terms dia kat situ. Nanti saya akan bagi example dia. Saya tak cover dekat sini sebab takut tak sempat untuk move to the next one. Okay, any other questions? Tak ada Kalau tak ada kita take a 5 minutes break, boleh?
Okay, Doktor. 5 minute breaks.
Okay.
Tahu ke?
Okay, welcome back to second session for this set lecture. So, Dr. Irfan, you can continue.
Can we continue now? Yeah. Can you hear my voice?
Yes.
Okay, so we're now moving to the second
Yes.
part. Okay, thank you. So we're moving to the second part of the, of the properties of a good estimator. So the second properties of a good estimator is called consistency of the estimator. So we always start with a definition first. So the estimator, or the statistics, we call that the estimator, the theta hat is considered a consistent estimator of the parameter of interest, the theta, if and only if for each c more than theta, discrepancy of the theta here, of the estimator and the parameter the parameter of interest theta there, the limit of it, as the sample size grows large until infinities, the main discrepancy becomes small, and then the estimator can be considered as a consistent estimator. The difference between the unbiased properties and the consistency property of an estimator. Now we are talking about the sample size, the behavior of the estimator as the sample size increases or grows and approaches infinity, as the sample size grows very, very large. Before this, we never talk about the sample size. Before this, I always say that, okay, n equals to 100, n equals to 100, n equals to 100. So the sample size we fix the sample size. In this case, we want to see the behavior, for example, the sample mean for the blood pressure. What will happen as we increase the sample size? Does it like going to converge? Nearer and nearer to the population blood pressure, or is going to deviate away, or what? In terms of the consistency of the estimator. Okay, so when you talk about the equation like this, it's always difficult to imagine things. So that's why I try to summarize this in plain English. So imagine you are estimating a true value of a parameter of interest. Let's say the real value of a parameter is theta, for example, the true mean of a population of the condition of interest or quantity of interest, systolic blood pressure, the blood pressure, the blood glucose, and then even the age of the patients in certain areas, or anything, or the prevalence or the proportion of people with kencing manis, diabetes, in state of Perak, can be anything. So because you don't know the actual value in the populations, of the condition of interest, for example, like your blood pressure or your blood glucose, so you use your sample and calculate some estimate, calculate some estimates, some estimator, not estimate, you calculate some estimator, estimate of their estimator here, for example, like sample mean. So, for example, and then what will happen if you have larger and larger sample size for your samples? For example, you repeat this process and observe with more and more data, what will happen to your sample mean? Is it going to be nearer and nearer to your population mean or not? First, you use your 10 observations, or we call that, data points or data. And after that, you took another 100 observations or data point. In this case, for example, 10 patients, and calculate the blood pressure. And after that, you take 100 observation and see the blood pressure. And then 1,000 observation. And after that, 1 million observation, and see what happened to the sample mean. Is it going to converge, or is it going to get nearer and nearer and nearer to the population mean for the quantity of interest, for example, your blood pressure or your blood glucose? So in this case, in plain English, the consistency of the estimator, the consistency of estimator means that as you are getting closer and closer to the truth, or to the truth for your quantity of interest, as your sample size grows larger. In this case, as your sample size n approaches to infinity, or in this case, just imagine that it grows larger and larger and larger and larger, then the estimate of the estimator theta hat here should get closer to the true population values, to the actual values of the quantity of your interest. For example, your population's blood pressure, or your population glucose level, or the age of patients. in your in para, for example. So that's what it means by, as the sample size grows larger, then the discrepancy or the difference between the the estimator and then the values of the estimator here and the actual values of the parameter in the populations, less than some very small quantity here, will be one. I mean, the probability here. In plain English, it means that the probability that your estimator theta hat here, for example, sample mean, is within a small distance c of the true value of theta becomes almost certain. That's the reason why, I mean, the probability here is close to 1 as you get more and more data, And that's the reason why in research, this is a good teaching point here. In research, that's the reason why we require, I mean, more data means that better results. Because, I mean, as we get more data based on if the estimator is consistent, then it means that more data means that we will get more accurate results, and the results will be very, very much close to the true values of the parameter of interest compared to if you use a small sample size. The more the better, because the more observations or the more data you have, the more information. Okay. So as a medical example, suppose there's a scenario here. This is a hypothetical scenarios. Suppose a hospital wants to estimate the true average fasting blood glucose level, FBG, denoted by mu FBG here, mu FBG, among all patients newly diagnosed with type 2 diabetes. Type 2 diabetes ni kencing manis. So selalunya kita akan tengok apa glucose level or blood sugar level dalam badan pesakit after we ask them to fast for for how many hours at least for 8 hours, for example. At least for 8 hours, then the patient fasted, then dia datang ke hospital, then we take the blood, hantar ke lab and see what's the glucose level. Kalau dia exceed certain value, then the person can be considered as having type 2 diabetes ataupun kencing manis jenis kedua. Okay, in this case we have N patients where we take the values, the glucose level or the blood sugar level from their blood. I mean, we measure them. So we have like the blood sugar level for the first patient, the blood sugar level for the second patient, blah blah blah, third patient, fourth patient, until the end patient. And this can be considered as a random sample of N patients. Sorry for the multiple answer. It's for the N patients. So we can use the sample mean of the fasting blood glucose X bar FBG here to estimate the population fasting blood glucose. At first, in this case, if you test just 5 patients, we obtain the fasting blood glucose level from 5 patients. Your estimate of the population of fasting blood glucose level can be way off. Maksudnya jauh. Dia tak kena, dia jauh. Because you have small data points. But if you test 5,000 patients, the average you get is almost certainly very close to the average fasting blood glucose mu FBG here. If the sample mean here is a consistent estimator of the mu FBG or the population blood glucose level or blood sugar level. Okay, if sample mean is a consistent estimator. So as further example and illustration, I put histograms of simulation of 3 different sample sizes. First one, katakan kita take like 1,000 samples. Each of the sample tu contains n equals to 5, for example. Maksudnya sample size for each samples tu is 5. So we get these kinds of behavior. We have like 1,000 different means for the blood sugar level. As you can see here from the range here is pretty wide. It can be between 6.5 until 10.0. And then this is the line yang red ni is the actual population blood sugar level here. As you can see here, dia punya range tu besar. 6.5 until 10, and then in fact this the means too, the majority of them they don't really hit the actual population mean for the blood sugar level. Banyak ni, dia jauh kan. But what will happen after you increase the sample size to 100, for example? Then you can see that the range here becomes smaller and smaller. It means that as we increase the sample size, the sample means they converge to the true population values of the blood sugar levels. Okay, and then what happens if you increase the sample size for each 1,000 samples to 1,000 to 1,000 patients or to 1,000 individuals? So I can see that the range becomes tighter and tighter. And tadi 6.5 until 10 in terms of the sample means now between 8.2 until 8.45. And then it's very, and then the mean of the sampling distributions of the sample means here is actually here, which is estimates the sample the true population mean of the fasting blood sugar well here. As you can see, that's the reason why as you increase the sample size, if the estimator is consistent, then it will hit will converge more and more accurately to the actual true population. Jadi biasa ingat balik unbiasedness, kita tak talk about the sample size, we fix the sample size. Now we're talking about the behavior of the estimator tu bila kita increase the sample size. Okay, understand? Okay. Sorry. Okay. Right. So what will happen if the estimator, another estimator is not if the sample mean is actually not inconsistent estimator. That's an example. Okay, that's an example. So you can see that the true blood sugar level is around this region. So now this is represented by the dashed red line here. So sample size N still kat sini kat tepi ni jauh tak kena. Then if you increase the sample size to 100 and 1,000, it still could not converge or hit the true population mean for the blood sugar level. You can see here. So this is what happened if the sample mean is not a consistent estimator of the population mean. This is just examples here. So how can you investigate or determine that the estimator is consistent? So in this case, as a summary, we can, based on this theorem 6 here, an unbiased estimator theta n for theta is also a consistent estimator of theta if the limit of the variance of the estimator approach to zeros as the sample size grows large. Means that, like this one, as the samples grows large, the variance for each sample means it becomes tighter and tighter and converge towards the true population mean here. That's what the formula or the theorem said. That's all. Okay. So an estimator is a consistent estimator. As a recap, if it's an unbiased estimator, for example, sample mean of the target parameter, and then as the sample size grows, then the sampling variance of the estimator equals to 0. In other words, the sampling variance of the estimator becomes smaller and smaller as the sample size n grows to infinity. As you can see from here, as the sample size grows larger and larger, then the sample means will converge towards population mean. You can see from here, this for example, the spread of the sample means as it goes bigger and bigger, then the spread becomes smaller and smaller, because it's between 8.20 to 8.45 for a sample size of 1,000, and between 6.5 to perhaps less than 10, 9.9 for example, for a sample size like this, for a sample size of 5 for example. So that's what it means. So the estimator keeps hitting the right target on average unbiased, and its value becomes less spread out as more data is collected. This is what you call, this part is consistency. Okay. So recap the differences between unbiasedness and consistency. So what it means, on average, the estimate hits the true values, and then this one is while we fix the sample size here. but on average will hits the true value. I mean, there's no biasness. If the estimator has an unbiased property, consistency means that as sample size increases, the estimates gets closer or converge. We call that in mathematical terms, converge, becomes closer and closer to the true values as the sample size increases. In focus, the accuracy of the estimate in repeated samples of fixed size, for example, that's the reason why I say that n equals to 100, n equals to 100, n equals to 100, because we fix the sample size. Then the accuracy of the estimates as the sample size grows for consistencies. In mathematical form means that, I mean, the ones that I showed you before, expectations of the estimator will be theta for each sample for when each sample is fixed in size. But on the long run, if we compute lots of sample means, then we average the sample means, and it will definitely hit theta, the population mean. But in this case, this means that the estimator theta hat will converge. Will converge in probability. We call that P here. Will converge in probability to the actual ones, to the actual parameter as the sample size grows larger and approaches infinity. And then for unbiasedness, expectation mean of an depends on the expectation mean of an estimator, and then for consistency, it depends on the behavior of an estimator when the sample size increases. And then can it be achieved with small samples? I mean, small sample. Yes, some estimators are unbiased even for small n or small sample size. No, for consistency only applies as sample size grows larger. As a real life analogy, kalau siapa-siapa kat sini pernah main dart, baling dart nak kena dekat dia punya papan bulat tu. Throwing darts pada permulaan that are scattered. Throwing darts that are scattered, but their average location is at the bullseye, at the tengah-tengah tu, even from the start. From the start pun, sebab the estimator is unbiased, so the average of it will hit the bullseye. Tapi consistency is different. Pada permulaan bila kita baling dart tu, if the sample size is small, it can start scattered first kat luar, dia tak kena tengah-tengah. But as the number of throws macam increases, they will converge towards the bullseye. The number of throws can be considered as your sample size. As the sample size increases, then they converge towards the bullseye. Okay. Ni more like behavior of the throwers, and then is the behavior of the number of throws, something like that. Okay. Kalau thrower tu dia orang yang skillful, yang pernah main dart banyak-banyak kali, can be considered as an unbiased estimator orang ni, maka on average dia boleh hit the bullseye. Tapi this one, it depends on the number of throws of the darts actually. Okay. So as an example, number 19, we want to show that the sample proportion for a binomial distribution, this one is P hat, X now is the number of success divided by the number of by n, is consistent estimator of the population proportion or parameter P. Okay. First again, when you have this kind of questions, you need to extract as much information as possible from the questions. So first, we know that the X follows a binomial distribution with n and p, n and p parameters, where X is the observed number of successes. So we have these things. P here is the estimator for the P here. The parameter for these binomial distributions. Okay, we want to estimate these things. So in this case, we need to use the variance, the relationships or the well-known result for the variance. So the variance of the P hat here will be equal to variance of X over n here, because P hat here equals to Xn. Okay. So based on this relationship, variance of AX equals to A squared times variance of X relationship. So we can factorize these things, 1 over n times by X. So X is the random variable, so 1 over n can go outside, but we need to square it because this is the relationship there. So variance of x, again remember, for binomial distribution, the variance for random variables x that follows a binomial distribution, then the variance will be np times 1 over 1 minus p there. So we substitute these things into these things. So we can cancel out n here. So we will get the variance of the p hat here as p times 1 over 1 minus p divided by n. So okay, now we see that what will happen if we increase the sample size, under the n larger and larger, or it approaches infinity. Okay, so as n becomes bigger and bigger and bigger, and then somehow we fix here bigger and bigger, so the quantities above the numerator becomes smaller and smaller and smaller, and because of that, because of this increases, and somehow we fix here. So the quantity becomes, the whole quantity becomes smaller and then smaller and smaller. It will approach to 0 as this n becomes very, very big. So because of that reason, then we can say that the variance of the p hat of the sample proportion will goes to zeros, as this quantity in the denominator yang kat bawah ni, bawah pecahan ni, kat bawah ni becomes besar, like besar until it approaches infinity. Okay, so because of this, because we fulfill these conditions, then we can say that the estimator here, the p hat here, is a consistent estimator of p, because the variance of these things approaches zeros as the sample size grows. Okay, this is the solution for the first question. Okay, show that for a random sample from a normal Gaussian population, the sample variance given by this formula is a consistent estimator for population variance. Example 20. Ini yang saya cakap tadi. For that, to show you, the bias property, berapa yang bias dia. Dia akan ada berapa banyak bias kalau we use different estimator tu. Saya akan compare these results dengan this one, the same thing in the numerator, x1 minus x bar squared, and the sum of it divided by n. So kita nanti kalau kita divide by n tu, why these types of sample variance tu dia ada bias. Nanti saya akan tunjuk, tapi saya kena buat dia punya solution later. Okay. Again, for this examples, or for this questions, recall the non-distributional results that you have learned in your previous lecture. If a random variable xi is distributed as a normal distribution with a mu parameter and the sigma squared, or the variance parameter, then the scale version of the sample mean, the sample variance here, the scale by this term, scale by sample size minus 1 divided by the population variance, so dia akan distributed as a chi-square distribution with a degree of freedom n minus 1. In other words, the scale version of the sample variance as squared follows a chi-square distribution with n minus 1 degrees of freedom. So it is a well-known distributional result, which is, I think, Dr. Nasir has covered previously. So untuk kita show that this form is a consistent estimator for the population variance here. So we need to define a quantity Q. Kita solvekan the equation. So just say, we just say that n minus 1 divided by by sigma squared times sample variance here equals to Q. You can use anything that you want, Q ke J ke whatever here. So where Q, the quantity here, the whole quantity here is represented as a chi-square distribution, because this one kan sama, Q ni is represented by this one. So kalau this one is distributed chi-square, then the left hand side pun for sure is distributed by chi-square. By simple algebra, then we can rewrite this equation in a squared or in the sample variance form. So with a simple algebra, we can get this one. Okay, sigma squared divided by n minus 1 times by Q. So now we use the same method previously. We take a variance, we take a variance on both sides, because we need to prove these things, the limits here. So we take variance on both sides. The S squared there, the estimator there, the sample variance, and then we take the variance on the other side as well. In this case, using the same results like this one, same variance relationship like this one. Let me show again this one. Then we will get these quantities here. Okay, because this is the random variable. So you move outside, then you need to square the terms, square the term here. So what is the variance of Q? If Q is distributed as a chi-square distribution with a degree of freedom n-1, based on known result, then variance of Q is given by 2 times by n-1. So we substitute this value into the variance Q here. Then we solve the algebraic equation there. Then we will, then we will get this quantity here. 2 times by sigma square, sigma to the power of 4 divided by n-1. So we can make a conclusion. See what happens if these samples, if the n here grows larger and larger and approach infinity. Okay, we fix that sigma, the population variance to some known values here. As we increase n -1 here in the denominator, then we know that these quantities here will approach zeros, because this one is grows so large, becomes like 1 billion or 1 trillion or 7 trillion, all those things. Then the quantities here become smaller and smaller and smaller. So in this case, we can conclude that as the sample size grows larger and larger and larger, then the limit for the estimator, the sample estimator for the sample variance for the population will go to 0. This tells us that the sample variance becomes increasingly consistent with larger sample size, and it will hit the true population variance as the sample size or the n increases or grows larger and larger. Okay, so this is the solution for example number 20. Okay, let's go for another example, example 21. Let's say that we have another samples, another random variables, or another observation, another data, x1, x2, x3, xn. But in this scenario, then this can be considered as a sample, as a random sample of size n from an exponential distribution instead, not a Gaussian distribution, not a binomial distribution, but comes from the exponential distribution. So is x bar is consistent estimator for the exponential distributions with parameter theta. Then we define the estimator. Sorry, I didn't put the estimator there. The estimator is like this: a sample, the x bar, which is sample mean there. So you know that this is the usual formula for your sample mean. Okay. For step 2, you know that the properties of exponential distribution covered in your previous lecture. If a random variable is distributed as exponential distributions with a parameter theta, then the variance of these random variables will be equal to theta squared. This is well known distributional properties, or the properties of exponential distributions. Okay, in this case, we compute the variance of x bar. So we take the variance on both sides. So in this case, we know that if variance of x bar will be like variance 1 over of this quantity here. So based on the same results here, based on the same relationship there, then we can move 1 over n outside and square of it, and then this becomes the variance of x, sum of variance of x. Since we assume, okay, this is one important thing. Since we assume that xi, x2, x3, and until xn is an IID, all right? But IID means identically and independently distributed random variables. So sum of the variance, okay, here the sum of the variance here will be equal to the sum of the variance here will be equals to sum of the variance will be equals to variance x1, x2, plus variance x2 plus variance x3 plus variance x4 until variance xn. This is only true where the sample is IID. If the samples are correlated, then it's not true because you need to consider the covariance as well. Okay. So in this case, because the variance are the same, so when you have like n samples, so it will be equal to n times n times variance of xi. Okay, times a variance of xi. So because you know that the variance of xi here is equals to theta squared, then you can substitute that into the variance into the n times variance of x. Okay, because they are the same. Okay, so you put it there. So then the quantities here will be 1 over n squared times by n theta squared. So you can cancel out these things. So this will be the variance of x bar. I think for better illustration or for better explanation, I will put the identity here because I forgot to put it. This and then this can be considered as as a samples from IID exponential distributions. So based on this quantity, as the sample size grows larger and larger and larger, and you fix this theta, for example, to certain known values, then again this quantity will become smaller and smaller and approaches to zeros. And that's the reason why we can conclude that as n approaches to infinity as the sample size grows larger, then the variance of the x bar here will also approach to zero. Hence, x bar is a consistent estimator of theta. Okay, I really hope that Dr. Nasir will remind me to put the to put some notes here. I forgot to put it. Okay, so the last example for the consistency of estimator. So for example 22, now we just imagine that in this scenario that we have like another random sample x1, x2, x3 until xn but this one is distributed in a gamma form or in a gamma distributions. Okay, so gamma distributions has two parameters. The first one is this is a random sample. The first one is alpha. The other one is beta. So we have like two parameters now for gamma distributions. So that's why the reason exponential distribution is a special case of gamma distributions where it only has one parameter. Based on your previous lecture, hopefully you still remember that. And then the PDF for the gamma distribution follows these kinds of form. Okay, this one is the gamma functions of the parameter alpha. And this is we call it the random variables, and the exponential it's a times by an exponential functions of s, the minus x divided by beta there. And as you can see that from the gamma distribution, recall that the support, the random variables can only take positive values. That's the reason why it's more than zeros. And alpha and beta as the parameters should also like take positive values as well. That's the reason why we restrict the values of the parameters and the random variables or the support of the distribution for x. X is called the support of the distributions to quantities that are positive, larger than zeros and positive. And then we have this estimator. We call it beta hat. The estimator for beta there, which is x bar divided by alpha, is a consistent estimator for beta. So we need to show this. Okay, step one, you need to solve this problem step by step. So you need to know the properties of gamma distribution. First, let xi or the random variable x in this case, in this scenario, follows a gamma distributions with two parameters alpha and beta. Then remember that the expectations of x that follows a gamma distribution is given by a times beta there, and then the variance of it a times beta squared. So since x1 until xn are IID gamma with a parameter alpha and beta, hence sample means we want to test it's given by these ones, your usual sample mean, and the variance of sample means is given by variance of x divided by n, and then it's given by the quantities here. Okay, here's a variance of your sample means. So we write down our proposed estimator, which is this one for betas. And then now we try to compute the variance of betas and want to show that as the sample size grows larger, whether the variance of beta will be reduced or will approach to zero or not. So the variance of beta hat here is similar to variance of x bar divided by alpha. because this is our proposed estimator for beta. So in this case, because the random variables is x bar in our case, x bar, so we can use the properties of variance. We can factorize these things and move 1 over alphas outside and then square it, and that's the reason why we have this term. And then what are the variance of x bar here? So the variance of x bar here is given by these ones, because I mean the variance of x here comes from here. Put it there. So this is the variance of x bar of your sample mean, and then you substitute the values into these ones, and then you can solve this algebraically. You can solve out this term. So this is beta squared, and so the variance of beta, of the estimated beta here is beta squared divided by alpha times n. So as conclusion, if you increase the sample size n to infinities, or it grows, as the sample size grows larger and larger and larger, because you fix the these quantities beta squared and alpha, because they are not random variables, so because they are parameters. So as you increase the sample size larger and larger, then the variance becomes zeros. We approach the zeros. Hence, beta, the beta hat can be considered a consistent estimator of beta. Okay, so those are the solutions for the final questions. Any questions? Any questions, students?
No, Adriana? Yes?
Based on theorem 6, an unbiased estimator is also a consistent estimator, but is it possible for an estimator to be consistent but biased?
Consistent but biased.
Yes.
You remember that the Chebyshev inequalities that you learned previously. The Chebyshev inequality.
Yeah.
Okay. Right. Okay. All right. Based on the Chebyshev inequality, we usually the estimator can, we usually can show that from the Chebyshev inequality that if the estimator is unbiased, but it's unbiased, it also can be also somehow we can show that it's also consistent. For example, but however, an estimator can also be biased, but still consistent, because biasness is measure how far the average of the estimator from the true parameter. Okay, that's the thing you have to understand. So that's the real, based on my analogy previously, it depends on the thrower of the darts. The skillful, how skillful how skillful is the dart thrower, the person, orang tu dia skillful ke tak, unbiased. Tapi consistency is based on the properties of the sample size. Dia akan converge to the true population, actually to the true population. Tapi because of that estimator is also unbiased, is also biased, dia tak akan dapat hit the true population. Tapi as the sample size grows larger and larger, the discrepancy tu dia makin dekat dengan the true population parameter. Tapi dia tak boleh exactly hit the true population parameter because the bias is still there. So it can happen like that as well. For example, like your sample variance kan, your sample variance yang ada different formula. Let me show it here. Okay, this is your usual sample variance kan, betul tak? Ini adalah your formula here for the Gaussian distribution. Just kita tukar sikit sini. S squared kepada ni sama, term kat atas ni sama, tapi S squared, tapi yang kat atas ni sama, tapi n minus 1 tu kita remove 1 ni, kita buat divided by n sahaja. This formula is called the sample variance with Bessel correction. Itu dia nama penuh dia. Tapi the sample variance yang without Bessel correction tu kita remove 1 here. So this is an example where the estimator for the population variance tu is a bias estimator. Tapi as the sample size, as the n grows larger and larger and larger, for sure dia akan makin dekat dengan the true population variance. Tapi because this is a bias estimate, I mean, not this one, and with the n saja without the minus one here, the uncorrected sample variance tu is a bias estimator for the population variance. Dia still tak boleh hit the true population variance. So it can be a scenario where the sample the estimator is consistent. As they grows larger and larger, dia akan makin dekat dengan the true parameter of interest. Tapi because dia on itself, dia tu sendiri pun masih bias, maka dia tak boleh hit the true values. Dia macam ni lah, macam as we, contohnya saya dengan Dr. Nasir kan, katakan Dr. Nasir tu is a better dart thrower berbanding dengan saya. For sure that kalau kita throw the darts, makin lama, dia akan makin dekat dengan bullseye yang kat tengah-tengah tu. Tapi because Dr. Nasir tu lagi terror pada saya main dart tu, maksudnya dari segi ni, dia lagi unbiased berbanding dengan saya. For sure on the long run, on the average, bila dia throw tu, permulaan tu pun dia dah dekat dah dengan bullseye tu. Maksudnya kalau throw kali pertama kedua pun dia dah dekat sebab dia lagi skillful pada saya. Sedangkan saya ni kalau saya throw the dart tu, mula-mula lagi pun saya dah jauh daripada dia. So itu saya kata analogi dia ialah kalau unbiasedness ni ialah macam the dart thrower tu himself. Dia punya skill. The experience dia main dart tu. Yang the other one consistency tu ialah the number of throws kita baling dart tu. Siapa-siapa kat sini pelajar lelaki yang pernah main dart tu dia faham kot. Saya dulu pun masa saya belajar tu saya ada main dart juga dulu. So that's the example dia. So the answer to your question, the estimator can be unbiased, can be biased and but consistent. Dia akan ada. Contohnya ialah another formula for sample variance yang mana kat bawah ni kita divide by n instead of n-1. This one is called the sample variance with Bessel correction. Yang satu lagi kalau kita divide by n-1 is a sample variance without Bessel correction. Okay, harap perangan ni boleh faham
Okay, thank you, Doctor.
Okay, sama. Okay, any other question? Any question?
I think there are no more question. Betul?
Okay, so macam mana Dr. Nasir, kita nak proceed to the next one ke? Because saya bagi just introduction ni.
Introduction, okay. But because we also have another 10 minutes to 4 o'clock. So if you can explain a bit what is sufficiency estimate, properties of a sufficiency estimator ni in brief lah. I think that should be okay kot.
Okay. Sebab saya estimate ni saya just go through dua part je lah kot. Sufficiency history dengan like in the plain English lah. Supaya I mean at least students can get the concept lah. Is it okay?
Okay.
Okay. So property of estimators ni dari segi sufficiency, the sufficiency of estimator ni saya really like the history. Sebab kalau kita nak faham satu benda, kita kena belajar history dia, cerita dia macam mana kan. So the property of estimator, the sufficiency property of estimator tu, the start orang yang pertama yang develop this thing is the famous R.A. Fisher. Yang kalau kita pernah belajar Fisher exact test apa semua tu, inilah tuan dia, dan design of experiments apa semua tu nanti akan jumpa Fisher ni lah. Pada tahun 1920, dan actually konsep ni dia develop by two prominent statisticians, R.A. Fisher dengan Jerzy Neyman. Jerzy Neyman ni pun dia famous, nanti akan jumpa waktu belajar nanti later on akan belajar dalam Neyman-Pearson lemma. Dua orang ni, I mean the two statisticians that develop they develop the idea of sufficiency, and then Jerzy Neyman ni orang yang prove that the sufficiency ni mathematically through the factorization theorem, or is also known as a Neyman-Fisher factorization theorem. Pada permulaannya in 1920s, Fisher ni dia dapat idea that raw data may contain redundant informations. Maksudnya data tu ada. I mean, you have the data, but some data also can also explain the behavior of the other data. I mean the other data points, for example. So because of that, he thinks that some of the data tu, I mean the information some information in the data tu can be considered as redundant, ataupun kalau kita dah tahu another data tu kita dah ada some ideas about the data. So the information tu is not full lah. Segitu, maksudnya ada kira redundancy. Maksudnya dia tak perlulah benda tu. So based on dia punya intuition saja, without any mathematical proof, that's the reason why we say that kalau kata the idea is intuitive in plain English, dia idea tu memang idea dari segi logik, tanpa ada mathematical punya proof dulu. By intuitively, dia thinks that this feature thinks that a sufficient estimator or a statistics may exist where all information in the data can be summarized by the statistics without significant information loss. For example, kalau kita ada 10 data berkenaan blood pressure untuk 10 pesakit or 10 patients with diabetes mellitus, ataupun 10 orang yang ada kencing manis. So kalau kita dapat summarize the data to using the sample means of this blood sugar level, then the sample mean tu can be considered as a good summary of the information, all informations of from the data from these 10 individuals or 10 patients with kencing manis or diabetes mellitus. Okay, and then the summary itu mean it will not cause any significant information loss. So based on this idea, Fisher ni dia postulated or dia hypothesized, he thinks that without any formal mathematical proof, dia thinks that the likelihood functions, we have learned the likelihood kan, the likelihood functions of a joint PDF, for example, can be entirely written in terms of a sufficient estimator. And then later on in 1930s ataupun lebih kurang 10 tahun kemudian, Jerzy Neyman pun, who is also famous for Neyman-Pearson lemma, show that the likelihood function tu kalau dia can be written into can be decomposed mathematically, can be decomposed into a product of two different functions. Satunya function of sufficient statistic Tx, and a function that is independent of the parameter of interest, and then the second function, then the sufficient statistic is sufficient representation for the parameters of interest. So because of dia punya mathematical proof here ini, it caused the birth of the Fisher factorization theorem, which is the basic building block untuk prove that an estimator is a sufficient statistic, or the estimator is a sufficient estimator. This Neyman-Fisher factorization theorem yang saya rasa nanti akan covered by Dr. Nasir later on, is a very important concept in statistics. Kalau siapa-siapa yang nak buat research later ke apa semua, it's a very important concept in statistics, because dia is a basic building block for Rao-Blackwell theorem or Rao-Blackwellizations of estimator. Maksudnya performance of an estimator ni, walaupun dia macam tu, it's not that very good initially, but we can improve the properties of the estimator, the consistency, whatever it is, kita boleh improve the performance of the estimator by conditioning the estimator to condition that the estimator on a sufficient statistics. Because of this, Neyman-Fisher factorization theorem ni is an important theorem where it will leads to the Rao-Blackwell theorem ni yang digunakan untuk improve the performance of certain estimator. Yang asalnya dia tak bagus, tapi dia akan jadi lebih bagus bila kita condition that on sufficient statistics. Tapi nak identify whether the statistics or the estimator tu is sufficient, then we need to use the Neyman-Fisher factorization theorem. So this is the basic, this is the first results that we need to use, the first theorem we need to use before we proceed to Rao-Blackwell theorem. I use a lot Rao-Blackwell theorem during my PhD lah untuk this one. Okay. So sufficient estimator, if the estimator utilizes all the information in sample relevant to the estimation of theta, then the estimator can be considered as a sufficient estimator. So I skip this part, okay? So I skip this part because this is more like a mathematical explanation. Tapi in plain English, what does it mean? Why does this matter? We call that. Kenapa pentingnya ada sufficient estimator ni, sufficiency for estimator? Because sufficient estimators are available because sufficient estimators are available because they summarize all the data needed to estimate the parameter. Maksudnya dengan ada satu je kuantiti, satu je nombor ni, dia akan summarize all the information in the data tu without any loss, without any significant or critical loss of information from the data. So in this case, somehow we can say that, generally speaking, we no need to keep the full data set. You can just use the sufficient statistics or the sufficient estimator to summarize your data sets. In other words, to emphasize the point, sufficient statistics enable kita, statisticians, to ignore the rest of the data once a sufficient statistic is known and used for describing or for summarizing our data. Okay, the last one as a real example for sufficient estimator. Consider a clinical trial test. Clinical trial ni maksudnya satu kajian klinikal yang mana a new drug tu kita nak investigate satu jenis ubat baru yang boleh menurunkan tekanan darah. That can reduce the blood pressure. Let's say that we measure the blood pressure reduction. Maksudnya bila kita bagi drug tu, kita bagi ubat tu, let's say we measure the blood pressure reduction from a sample of N100 patients with high blood pressure, for example, berapa dia punya penurunan tekanan darah tu, blood pressure tu. So setiap satu patient tu kita adalah penurunan blood pressure dia. Mungkin yang ni turun 10, yang ni turun 5, yang ni turun X3 ni pula dia turun 12, yang another one turun 14, turun 20 pun ada, mungkin turun 6 pun ada, sampai lah X100 tu mungkin turun 4 mm mercury lah, dia punya tekanan darah tu turun. So in this case we want to estimate the true average blood pressure reduction true average blood pressure reduction at the population level, which is the true population mean blood pressure reduction. So consider satu estimator ni, nama dia sample mean for the blood pressure reduction. Is considered a sufficient estimator for mu if the sample comes from a normal Gaussian normal distribution with known variance. So this means that if we know the X bar here, the sample mean here, gives us all the information in the sample yang ada 100 orang ni about the mean reduction, and then we don't really need to look at the individual blood pressure, individual patient's blood pressure reduction anymore, because the X bar tu dia summarizes the data here really well without any significant loss of information. To recap, untuk as a summary, sufficient estimator means that it captures all data, all information in the data that is relevant to the estimations of our population, of a population parameter of interest. For example, in this case, population mean blood pressure reduction in our hypothetical kajian klinikal di sini, without any significant loss of information. This example that I told you previously. And then the usefulness of a sufficient estimator tu is more than the raw blood qualization. It has been used in many applications. For example, in medical statistics, economics, machine learning, and even in Bayesian statistics, my specialty. Especially kalau kita nak pakai satu algorithm dalam Bayesian statistics ni, yang mana dia dipanggil adaptive Bayesian computation or ABC algorithm. In this case, adaptive Bayesian computation is a very advanced algorithm, yang mana kalau siapa yang ambil Bayesian statistics punya specialty, during the degree level or master's level, you will learn about this adaptive Bayesian computation, which is a type of simulation tapi faster than the usual algorithm used in Bayesian statistics. So for me, personally, sufficient estimator is a very important part yang perlu kita faham, yang perlu kita tahu in terms of dia punya teori, because the application will be massive atau will be vast in the future. So saya stop kat sini je, sebab takut tak sempat. Sebab ni pun dapat 3 minit. Terima kasih. Thank you all. Any other last questions from the audience?
Yes, student, do you have any question? Last question for Dr. Irfan regarding the topic, especially on unbiased and consistency estimator.
Apalah, untuk set the stage last kali kan, untuk before Dr. Nasir continue with the next class. This is we call that the Diemann-Fisher factorization theorem. This is the theorem itself. This one. So kalau kita write the likelihood functions into like this is the likelihood functions, then we can decompose the likelihood function into two separate functions here. This one is based on the functions of your data only. This one is based the functions of your sufficient statistics given your true population parameter. Itu untuk set the stage, nanti Dr. Nasir akan explain further. But remember, this is the theorem.
Ya, kita akan tengok theorem ni dalam chapter number 5 later. Okay. Okay, we have come to the end of the session. Thank you very much, Dr. Muhammad Irfan. And thank you all for joining today collaborative teaching session on properties of good estimator under STA 256 Mathematical Statistics 2. It has been a privilege to moderate this session. And I hope you found the insight shared by Dr. Muhammad Irfan both informative and inspiring lah. So his expertise has enriched our understanding to the important topic, and his contribution reflect the strong academic collaboration with University Teknologi Mara and the University Kebangsaan Malaysia. As we wrap up, I encourage you to reflect on the key point discussed today and apply it in our study. So for those who have additional question, so please feel free to reach out Dr. Irfan later on, or you can contact me in class, and the session recording and material will be available via my YouTube channel for your reference. And please do subscribe and click on bell button. Right. Once again, sincere thank you for Dr. Irfan for his time and knowledge, and to all of you for your active participants. So wish all the best on your academic journey, and until we meet again, take care. Assalamualaikum. Thank you very much, Dr. Irfan.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih, Dr. Nasir.
Okay, insyaAllah.